G'day, welcome back to our discussion of trigonometric functions. We started last time talking about how we define angles, and we introduced the idea of the radian and the degree measure, and we're almost always going to be using radians from now on. So we're looking here at an angle t that's defined on the unit circle, and the unit circle here has a radius of 1. The angle t bisects the unit circle at a point P, and I'm calling that P of t because it depends on the value of t. If t was the angle 0, then we'd be dissecting at a point there, and so that would tell us that P of 0 is equal to, well, the coordinates of that point is just 1, 0. So P of t is a coordinate. This is P of, well, something. The coordinates of this point is 0, 1. We're just here on the y-axis, so x is 0, y is 1. And the radian measure to that point is pi over 2. So P of pi over 2 is 0, 1. So we can define this point, and we can find P of t at various points. And what we're going to do is define that to be two new functions. We're going to define this point here to have coordinates given by two new functions, sine and cosine. And what this means is that I'm essentially introducing a distance along here, and that's the x-coordinate of this point, and the x-coordinate of this point I'm calling cosine of t. And the y-coordinate of that point, this height here, I'm calling sine of t. And every point on the unit circle is going to be given a point, and therefore will have a value for these two new functions. And these functions are called cosine and sine. All right, so looking at the unit circle, if I pick any point on the unit circle and I get a value for sine and cosine, here's a value on the unit circle, the coordinates of this point is going to be cosine, I'm going to call it t prime, sine of t prime, where t prime is the angle I'm measuring. In radians, remember, from the standard position, the coordinates of this point, whatever it is, are going to be given by this cosine and sine function. And that means that this length, well, I know this length, I'm telling you I'm giving this length along here as cosine t prime. The length along here is sine of t prime, and the length of the hypotenuse of this right triangle is 1, because this is a unit circle. And so we've always got the Pythagorean identity. And this identity is coming directly from the circle we're looking at, because we're looking at a circle which has radius 1, and so we've defined these two lengths to be the cosine of the angle that appears here and the sine of the angle that appears here, and 1 along here. So the length of this squared plus the length of this squared must equal 1 squared. And this gives us our first identity and real important understanding of what sine and cosine mean. And when we write this, instead of writing the parentheses and the squares, we usually put the squared in here. But this means cosine of t all squared. And cosine of t is just the x-coordinate of the point. Sine of t is just the y-coordinate of the point that lives there. So the coordinate of this point is cosine of t, sine of t. Let's do some examples in a sec, but before we do, what's the domain? Well, if we're just plugging in these values of t, they're just real numbers. They're real numbers because t is the angle. And we can keep measuring around and around this circle. We can make t as large as we like. We can measure clockwise, and so t can become as negative as we like. So the domain of both sine and cosine is all real numbers, because the angle that we can plug in here, this t, can be any real number. Similarly, the range, well, the range is the x and y values. These are the values that are coming out of the unit circle. If I pick any point on the unit circle, the biggest the x value can get, here's the x value, the biggest the x value can get is 1, going this way, or minus 1, going that way. The biggest the y values can get is 1 up here and minus 1. I'm just thinking about the points on the unit circle. The very biggest x value is over here, it's when x is 1. The very smallest x value is over there, it's when x is minus 1. X values are what's coming out of the cosine of t. Y values are what's coming out of the sine of t. And so the domain and range of both of these functions is minus 1 to 1. So let's look at some examples. Okay, so we already know some simple points marked on this unit circle. We've got the point 1, 0. We've got the point here, which is 0, 1. Over here, we've got the point x is minus 1, y is 0. Over here, we've got the point x is 0, but y is minus 1. So we can use this to very easily calculate some values of the sine and cosine functions. And so here we go. This first point, the angle that this ray makes with the positive x-axis is 0. The point we're looking at the end, where it intersects the unit circle, is the point 1, 0. That means cosine of this 0 is 1, and sine is 0, because we're just looking at the x and y coordinates. X coordinate is cosine, y coordinate sine. In other words, the cosine of 0 is equal to 1, and the sine of 0 is equal to 0. These two things are coming out of that column. That's all I'm writing. And notice that cosine of 0 squared plus sine of 0 squared is equal to 1, which agrees with that identity we had last time. If we go up to this second point that we marked, this is an angle of pi over 2 from the positive x-axis. It's the point 1, 0. So at pi over 2, the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. We can keep going. We can go over to this point. This is when we've got an angle pi from the positive x-axis. We're measuring that angle. And in that case, we're talking about the point minus 1, 0. So the cosine of pi is minus 1, and the sine of pi is 0. Going around to our last point here, we see that cosine of, and remember this is 1.5 pi, so this is 3 pi over 2. The cosine of 3 pi over 2 is 0, and the sine of 3 pi over 2 is minus 1, precisely because that's the point 0 minus 1. The x value is the cosine. The y value is the sine. So working these things out is very straightforward. These are some very special values, and you should be able to sort of observe them. We could also continue traveling around the circle, so we could go 2 pi and then another pi over 2, and we'd see that the values would be the same. So in other words, the cosine of 2 pi plus pi over 2, well, that's going to be exactly the same as the cosine of pi over 2. Remember these two angles? We called them coterminal. 2 pi plus pi over 2 and just pi over 2. Those angles are coterminal. Their cosines will be the same. We're talking about this point, so the cosine is the x value, that's 0. Similarly, the sine value. And this gives us an idea that every time we do a full loop, every time we go 2 pi around the circle, the sines and cosines are going to be the same, because sine and cosine are periodic. So this shows us that sine and cosine are 2 pi periodic, and we can see here what that means. If you add 2 pi to the value of t, then the values that come out of sine and cosine are exactly the same as they were for the original value of t. And all that means is we've done a complete loop around the circle, so we're talking about the same point on the unit circle. So of course the values coming out of sine and cosine, which are just the x and y coordinates of this point, will be the same. We can generalize this idea, and we will talk about functions later, that are p-periodic. So they're not just 2 pi periodic. This is an example of a function that's 2 pi periodic. We'll be talking about functions that are p-periodic, which just means if you add p to the value, then you'll get the same thing as you did before you added p. This is all this is saying. And so we'll see examples of that amongst the trig functions. But the important thing to remember about sine and cosine is that they are 2 pi periodic. So let's have a look at a few other properties of sine and cosine. Imagine I've got some angle t. I can calculate the values of sine and cosine if I know this point on the unit circle. This is a unit circle. And instead of traveling t radians in the counterclockwise direction, I'm going to think about traveling t radians in the clockwise direction. So starting from our initial side, we'll end up at this point down here. And it's easy to calculate the x and y value. That's just cosine of minus t. Because that's what cosine and sine do. They calculate the x and y value. So the x value of this point is cosine of minus t, and the y value of this point is sine of minus t. But let's compare those 2 points. In fact, let's join that line up. Let's compare those 2 points, one at the top and one at the bottom. If I'd drawn it well, you would see that the x value here is exactly the same. Well, what's the x value again? The x value is just the cosine. So the x value is identical for these 2 points. So the x value down here, cosine of minus t, must equal the x value up there, which is the cosine of t. Looking at the y values, well, the y values are just reflected. The y value here is positive, the y value here is negative. The y value, in other words, of sine of minus t, that's the y value at the bottom, this y value. If I compare it to that y value, I find, well, they've just got opposite signs. So sine of minus t is equal to the negative of sine of t. And so this is an important property of sine and cosine for all values of t. If you think back to what we know about even and odd functions, we look at sine, anything that behaves like this is odd. So sine is an odd function and cosine is an even function. So we've learnt about sine and cosine a little bit more. So let's use a little geometry to find some information about these values of sine and cosine. We already saw the special values, the cosine and sine of 0, we use this point. The cosine and sine of pi over 2, we use this point. Let's think about the point right between. So the angle is 45 degrees here. The angle is pi over 4 radians. And because we see that, we see by the symmetry that the x and y values must be the same. So the x and y values of this triangle, in other words, must be the same. So because we've split the middle here. So we must have that the cosine of pi over 4 and the sine of pi over 4 are the same. And here I'm using the value t equals pi over 4. So this must be the same number in both the x and y positions. We know this is a unit circle, so we know the diagonal here is 1. So we've got the Pythagorean theorem, which told us that cosine squared plus sine squared was equal to 1. So just doing that when t is equal to pi over 4, this is our version of Pythagoras for trig. Because sine and cosines are the same, I can just say, okay, plugging in sine and cosine are the same. This is two lots of, let's say, cosine. Because sine and cosine are the same, so I'm going to call them both cosine. This is cosine squared, this is cosine squared. And so that means that cosine squared of pi over 4 is a half. And that tells us that the cosine of pi over 4 must be 1 over root 2. We know the x value is positive. The x value here is definitely positive. And so the coordinates of that point there are 1 over root 2 for x and 1 over root 2 for y. So that's the coordinates of the point. And put another way, here's two new values for the sine and cosine function that we didn't previously have. The sine and cosine of pi over 4 are not only the same, but they're both 1 over root 2. Let's look at a similar kind of construction. Here I've drawn what turns out to be an equilateral triangle, because if you think about the two angles I've got over there, pi over 6 plus pi over 6, well that's 2 pi over 6 or pi over 3. If you convert that to degrees, pi over 3 would be 60 degrees. And so we've got 60 degrees here. Which means this must be 30 and this must be 30, which can't be right. Okay, let's look at a similar setup. This time I've drawn a triangle here with an angle of pi over 6. If we just think about the part of the triangle that we can see on the top and bottom, it's a terrible version, but this is pi over 6. If you convert pi over 6 to degrees, that's the same as 30 degrees, which means I must have 60 degrees over here, that's pi over 3. So pi over 3 radians is the same as 60 degrees in degrees. Pi over 6 radians is the same as 30 degrees. So if you look at this triangle, I've got a 60 degree angle up here, a 60 degree angle there, and two 30 degree angles here. So this is an equilateral triangle. Every angle is the same. It's an equilateral triangle because it's got an angle of 60, 60, and 60, which means all the sides are the same length. All the sides are the same length, and, well, we know one of the sides. We know this side is length 1 and this side is length 1 because they're part of the unit circle. They're radiuses of the unit circle. So the distance from there to there is 1. And that means that the distance up and down here is 1 as well. And perhaps more usefully, I can think about the height up here as being half of that length, so it must be a length half. But that's the y value of this point. And the y value of that point is the value of sine of pi over 6. So that little argument tells us that the sine of pi over 6 is equal to a half. And we also know that the cosine squared of pi over 6 plus the sine squared of pi over 6 is equal to 1. And we know what sine of pi over 6 is. Sine of pi over 6 was a half. And we can rearrange that to tell us that the cosine of pi over 6 is the square root of 3 over 2. I did that very quickly, but this is a quarter, so when I subtracted on the other side we get 3/4, and then I took the square root to get the cosine of pi over 6 is the square root of 3 over 2. We know it must be that because the cosine and the sine value here are positive, so we choose the positive root. And so that gives us, again, a new pair of values for sine and cosine. Now, these ones we're collecting are special values and we're going to be using them a lot. Let's look at another pair. The last setup, we're using very similar triangles. We're going to use one triangle down here, which is pi over 6, another triangle up here, which is at an angle pi over 3. And so the angle, remember pi over 3 is 60 degrees, so the remaining angle in here is actually pi over 6. So the length that I have up here is the same as the height we have here. And similarly, the distance along this leg of the triangle is the same as the distance along that leg of the triangle. And when we put that together, we see that the cosine of pi over 3 is going to equal the sine of pi over 6. Because the sine of pi over 6, well, the sine of pi over 6 is the y value for, this triangle. So we're talking about that length is the sine of pi over 6. And we see that that's the same as that length. But that's the x value for this point, cosine of pi over 3. So the cosine here, this x value, is the same as the y value down here, and the y value down here was the sine of pi over 3. And we just calculated, the sine of pi over 6, and we just calculated that. We just calculated the sine of pi over 6, and we found that it was a half. And similarly, we can turn this around and say that the sine of pi over 3, this y value here has to be the same as this x value along there. That x value is the cosine of pi over 6, and we just found that was the square root of 3 over 2. And so we've got another pair of points. And that completes our special values that we really should know as we move forward. And in fact, we can put them all in the one table. We already found that the sine of 0 was 0 and the cosine of 0 was 1, so we can fill those in. We did similar for pi over 2, and we just found pi over 3. Pi over 3 is a half. Cosine of pi over 3 is a half. So this is a half, and this is root 3 over 2, and this is 1/2, and root 3 over 2 the other way around, because we just found it. We just saw the symmetry, and that lets us fill in all of the values in the table. And I expect you to know these. These are the key values that you should know off by heart. Our final idea today is that of reference angles. And the point of a reference angle is it lets us take angles that are in quadrants other than the first quadrant and map them back and think about the values of sine and cosine in the first quadrant. And we've just calculated a bunch of sine and cosine values in the first quadrant. So here's an angle that I've drawn in the third quadrant. Remember, the quadrants are given by, you can think of them as the sine, the SIGN, where the x and y are positive and negative. So in the first quadrant here, x and y are both positive. Second quadrant, x is negative, but y is positive. Here they're both negative. In the fourth quadrant, we've got positive x again, but y is negative. So if we're down here in the third quadrant, like the angle I've drawn, the angle T in standard position, then P is in the third quadrant. And the position, the coordinates of this point are just cosine of t and sine of t, because that's how we define sine and cosine. So the cosine of t is this length. The sine of t, I got that the wrong way around. The sine of t is this length, and the cosine of t is this length. And if we wanted to calculate those lengths, we just plug that value t into sine and cosine. But I can define this thing called the reference angle using an acute angle that the terminal side makes with the x-axis. So in other words, I'm talking about this angle. This is the acute angle, so less than pi over 2, made with the x-axis. And if I think about drawing that, continuing this line up here, this is the same line, and so this is the angle t prime up there. The angle t prime here is the same as the angle t prime there. So you can see that the height above the x-axis here is the same as the height below there, except over here we've got a negative. And that tells us something important. That tells us that the sine of t is this distance, which is a negative, is going to be the same in magnitude as the sine of the reference angle, the sine of t prime, because the sine of t prime is this length here. The only difference is we need to know what quadrant we're in, whether that's positive or negative. Here we can see the sine is the opposite. Sine is going to be negative, whereas up here, this length is sine of t prime. Sine of t prime is going to be a positive number. Sine of t is going to be negative, but their magnitude is going to be the same. We can make the same argument with cosine of t. This length here is going to be the same magnitude as this length here, because this is the cosine of t prime. They're going to be the same, except in this picture, because we're in the third quadrant, this cosine of t is going to be negative, because we know x is negative, and that means cosine of t is negative. We know y is negative, so we know sine of t is negative. And we can go around and write that in every quadrant. So if I give you an angle t in the first quadrant, sine and cosine are both positive. If I give you an angle t in the second quadrant, the cosine of t will be negative, the sine of t is positive, and so on. So back to our example, this cosine t is a negative number, but the magnitude of it is going to be the same as the cosine of t prime. So all we need to do is find the, sorry, that's a cosine. All we need to do is find the cosine and sine of t prime, which are in the first quadrant, and then decide which quadrant we're in with t, with the angle t, and that tells us whether we take the positive or negative. So this sign here depends on the quadrant. So let's look at the cosine and the sine of 2 pi over 3. 2 pi over 3, that's 2/3 of pi. Here's pi. So 2/3 of pi is going to take us to there somewhere. So here's our angle, t. It's 2 pi over 3. We're looking for the cosine and sine of 2 pi over 3. In other words, we're looking for the x and y value of this point. I can't write small enough to get this in, but 2 pi over 3 are the x. Sine of 2 pi over 3 is the y value here. Cosine of 2 pi over 3 is the x value. You can see the x value is negative. The y value is positive though. And that's because 2 pi over 3 is in quadrant 2. And we just decided that in that region, cosine is negative, sine is positive. So we need to find the reference angle. The reference angle is here, or really I should point it in the other direction. The reference angle is there, it's t prime. And notice that if I take this angle, add on t prime, I get pi. In other words, t plus t prime, just looking at the picture, is equal to pi. And I chose this because this is an acute angle with the positive x-axis. And that's what I'm always looking for. In other words, t prime is supplementary with t because they add to pi. Well, we know what t is. T was 2 pi over 3, and I'm looking for t prime. So I've got 2/3 of pi, I add t prime, and I get pi. So t prime is pi minus 2/3, and that's 1/3. So t prime is pi over 3. And so we can immediately use what we wrote down in the last page, which is that the cosine of 2 pi over 3 is either going to be positive or negative the cosine of pi over 3. And in this case, we're in quadrant 2, so the cosine will be negative. The sine of 2 pi over 3 will be either the positive or the negative of the sine of pi over 3, because pi over 3 is the reference angle. All I'm using here is the reference angle. And I can look up in the table. Sine and cosine of pi over 3 are up there. So cosine of pi over 3 is a half, so this is minus a half, and this one is root 3 over 2. So that gives you an idea of how we can use reference angles to calculate sine and cosine in other points, at other points that aren't just these simple ones, but we can use these simple points. All right, so have a go at the pre-class assignment and we'll talk a lot more about these ideas.